Yes? I want to give one more. And then we have, do you remember the power rule for the first thing we met? The first method we ever learned? We have a generalized power rule. But I want to show you a couple more of these before I give it to you. So how about this? What if I have that? Well, let's talk about it first. How would you do this? It looks like almost three functions, doesn't it? Doesn't it look like a function within a function within a function? Like you could say that this is being plugged into a root, right? But the root is being plugged into a 1 over something. Like it looks like it might be three functions. Yeah, this is a better approach. How about this? Rewrite this, first of all, as this, 1/2. Right? That's 1/2 down there. Then bring it up, and the whole thing comes up, right? The whole expression comes up as negative 1/2. And now, does this look like a function inside of a single function? Function inside of a function. So I'm going to get my towel again. It's coming in real handy today. And I'm going to just cover this up, because that's the inside, right? The outer function is, I'm raising something to the negative 1/2. So what would be the derivative of that? Negative 1/2 pops out. And then I'm going to take this green towel, whatever it was, and raise it to the negative 3/2, because that's what the power rule said. We bring the power down, subtract 1. What was in here? This, x squared plus x plus 1. Chain rule, are we done? Nope. Times the derivative of what's inside, 2x plus 1. Do I need that in parentheses? Yes. And that's it. That's the derivative.
I guess if you wanted.
Yeah, you could mess with that, but... All right. I want to keep us on this same track. We have avoided, on purpose, triple compositions, something within a function and within a function. We've avoided those. So what about if I take sine of cosine of x squared plus 1? So this is where method 3 completely blows the other methods out of the water, because this is actually a function, x squared plus 1, inside of a second function, which is all inside of a third function, which is all inside of a fourth function. So you actually have 4 compositions here, right? 4 pieces to this. And if you did this using f and g, it would be pretty confusing, because the f and g works great when you have 2, right? What if you have 3? And I avoided that on purpose because I wanted you to see how we can do this with the short method. This might be a little hard. I said it's like an onion, right? Where do we always start with an onion? Outside layer. What is the outermost layer of this onion?
Sine x.
That's sine x on the outside. So for my derivative, I'm going to look at this as being sine of, and I don't know if I have anything long enough for this. I think maybe I can use the hypotenuse of this towel. There we go. It's sine of all that little bandana, right? Right? What's the derivative of sine of all of that junk? And I think I might even highlight what I'm talking about. This is all the junk, right? The derivative of sine of all that red stuff should be cosine of all that red stuff, junk, which is sine of cosine of x squared plus 1, close, close, close. You see that? Am I done? No, chain rule says now I just come in and multiply by the next layer in. So I've done this layer, right? So now I'm working into the next layer. The next layer is what? You peel back and you see another sine, don't you? Another sine. It's going to be sine this time of this blue stuff, right? Now that's the stuff that's inside that second sine. So the derivative of this second sine will be cosine of the blue stuff, which is cosine of x squared plus 1, right? And we keep chipping away at it. We can now peel this one off, right? That's done. The next layer in is cosine. The derivative of cosine is negative sine. So be careful here. I'm going to go like this. Times, be very clear on this. Parenthesis, negative sine of what though? X squared plus 1. Don't lose track of where we were. We were on cosine of my hand. And the derivative of cosine of my hand is negative sine of my hand. That's my hand. So we're here. That cosine's done. We finally made it to the inside of the onion. The derivative of the inside of the onion needs to go here, which is 2x. That is the derivative. You could pop the 2x out to the very front and you could bring the negative with it. That's how the chain rule works. Yeah. Questions? What the graph of that looks like? Yeah. All right, so there is a generalization that we can use because a lot of times when we're using the chain rule, that whole power thing where I'm like the tau to the power and the power pops out, right? That happens a lot. So we have a generalization that we can use. Remember this? Do you remember the power rule? It said that if we have x to the n, that the derivative of this was nx to the n minus 1, right? And I proved that to us using the limit and everything. We used Pascal's triangle and we were happy. We saw, yes, I agree, that works. But now we have a general power rule. A general power rule uses, general power rule. The general power rule incorporates the chain rule with it. So it would look like this. Instead of saying we have x to the n, let's just say we have anything to the n. We'll call it u to the n. All right? And we're taking the derivative of u to the n. That u is my tau, or my mouse, or Laura's paper, right? Something to a power. Then the derivative of that should be the n, the u to the n minus 1. So you're going to do everything you did before. Drop the power out. You're going to reduce the power by 1. But then chain rule says you now need to tack onto this the derivative of what was there, right? And the way I could write that is like this, u prime. So it's the power rule, but don't forget to take the derivative of what was there and tack it on with multiplication. Okay? Sure? So I want to go back to a problem that we did before, x cubed, and we want to take the derivative. Does this still work with this new formula? Let's try it. So I'm going to cover up, I'm going to say that the x is my mouse, okay? So what's the derivative of my mouse cubed? 3 mouses, what's my mouse? X squared times chain rule, right? What's the derivative of what was there? What's the derivative of x? 1. If I tack a 1 on, is it the same answer? That 1 was always there, but we didn't talk about it because we didn't have chain rule yet. That 1 was there though. Now when we do problems like this, I'm going to do one that's similar underneath this. If I take the derivative of sine x cubed, instead of just x cubed, take its derivative, we're going to have the 3 pop out. Sine x is going to get what? Squared, but we've got to tack on the derivative of what was down here, which is cosine x. And then we have to take the derivative of what was inside this, which was what? x. What's the derivative of x? 1. So there is a 1 that's always on the outside of this that we never even really talk about, but it's always there. But that's it. How do y'all feel? I mean, I've been trying to teach chain rule for a long time, and I've tried so many different things, and it's so dependent on the person. Y'all feel okay with this? Like you feel like you're going to be able to go home, practice, and
I want to see method 2.
you want to see method 2 because you're hoping it'll be even better, or just you want to see the notation? Okay. All right, I think we can leave it at this. I don't think there's anything else that I need to show you example-wise. I was doing the homework for the homework solution videos, and I was thinking, I did like different problems, you know, and I was thinking, you know what? You, as students, should do every problem, number 1, all the way through, probably 1 through 48. You should do every single problem. There's no such thing as doing too many chain rule problems. It's absurd to say something like that, all right? You should try and do all 48. So that later on down the road, you're not sitting there going, well, you know, I'm just trying to understand the chain rule, but I haven't really practiced all the problems. You should practice as many as you can. I even thought about offering it as a bonus, that you turn in all 48 problems, but I shouldn't have to motivate you with bonus to make you do work, right? Or is that the way it works? It's the rabbit in front of the dogs chase the rabbit, right? On the tracks?
Yes, but there's always incentive for mine.
Yeah, you're right. Let's just say that if someone were to come in and turn in all 48 problems to me all nice and neat and written, and that I would be highly impressed, almost moved to the point that I would maybe consider something.
Hint, hint.
Perhaps. And it will probably make you ask questions too, like, I'm not sure how to do this one. Because if you look at the book's examples, okay, I went through pretty much the book's examples, and if you look at them, there are some problems in the homework that those examples just do not get you ready for. Right, so you have to actually get in there, and the author of the book is expecting that you're going to have to grow with your whole concept of chain rule as you work through these problems. You're going to have to develop a more sophisticated perspective, I guess, of how this all works. All right, here we go. We're going to look at method 2, but I think we'll only look at it just for its importance with the notation. All right, so just remember that when we've said y prime in the past, this is what we've meant. That was Leibniz's notation for the same thing, right? It said, what's the instantaneous rate of change in y with respect to x? And I told you that came from the little idea of rise over run. But that was the derivative. It's the slope of the tangent line. What's nice about Leibniz's notation, though, is that it always includes not only the dependent variable, but the independent variable. So like if I write down as an example that first one, y equals the square root of x squared plus 1. That was the first one I did today, right? If I write that down, we would say that y depends on x. Y is a function of x. So in Leibniz's notation, you can tell the numerator, right, this little y is your dependent variable, and the x is your independent variable. The y prime here, it's just understood to mean this. But you can't see the x in there, can you, in this notation? All right, so let's say I want to take derivative of that. This is the way Leibniz approached it. He still said, hey, look, I've got layers of functions here. Function within a function within a function. But he approached it like this. He said, look, I'm going to say that this y is really like the square root of something, u. Okay, do you agree? This looks like the square root of something. And that something in there, that inner piece, I'm going to call u. Then he wrote down below this, well, u is just x squared plus 1. Do you agree? If I just take x squared plus 1, I call that u, then plug it in here, then I get back this. Yeah? And then he said, I wonder how I could use these to get that answer. I want dy dx, right? That's what he wants. He wants dy dx. And he realized, wait a minute. I could rewrite this like this. So he introduced like a 1. Okay, the 1 here is du over du. Do you see that these du's would cancel out? Yes? And then you'd be back to this. What does this mean? Take the derivative of the function y with respect to u. So that's, where do you have an equation that has y in it where y depends on u? Where is it? Right there. This right here is the equation that shows how y depends on u. Isn't it? And this right here, du dx, would require that we have an equation that shows that u depends on x, which is this. Right? Do you all see that? So now what I'm going to do is I'm going to just look at this and take what is the derivative of y with respect to u here. So what's the derivative of the square root of u, everyone? 1 over 2 root u. Okay, what is the derivative of u with respect to x? So what's the derivative of x squared plus 1? 2x. Okay, so this piece right here is this, right? And this piece right here is this. And so what's dy du according to us? Dy du is 1 over 2 root u, and du dx is 2x. Is that almost our answer? Almost the answer? The only difference is that we have u's in here. We're supposed to have all x's. But what is u? X squared plus 1. So if I replace that with x squared plus 1, that's the answer. The thing about Leibniz notation that is nice is it shows you the chain part. It shows you you're taking the derivative of the outer function times the derivative of the inner function. You can kind of see it in there. I'll do another one. How about the sine squared x? Or it was sine squared x, which we said was sine x squared. Leibniz would have looked at this and said, all right, I have an outer function, inner function. The outer function is something squared. And he would use u probably, u squared. And then he would say that the u that I have here is what? Sine x. And then he would realize that if I just take these derivatives, right, what are the two derivatives he would have here? This one would be dy, d what? du. This would be 2u. And then this one would be du dx. This would be cosine x. And he knows that these two multiplied together is dy dx. So if I multiply those two together, I would get 2u times cosine x, but what was u? Sine x. So you get 2 sine x cosine x. Do y'all like that method? No? I like this method personally. I mean, I really do. I've actually taught classes in Cal 1 where I just present this as the method, and then I do the shortcut method later, and I don't even go through the other one. But I've tried it all, okay? Every student's a little different. Let me give you another one. How about something like this? Haven't seen anything like this yet. There are lots of little domain issues we would have with this function. This is a weird function, but don't worry about it. Let's just try and find the derivative. So if we were Leibniz, we would say y is equal to square root of u. But u would be the stuff under the root, right? Is actually sine of something else, right? So call it maybe sine of v or w or r or whatever you want to call it. That v kind of looks like an r. We'll just leave it. And then the v is what? X squared plus 1. So you've got this 3 layers to this, right?
So then you need to take the derivative
Of each one. This one would be d what? dy du. This one would be du dv. And this one would be dv dx. And we'll do each one of these now. We get 1 over 2 root u. This one is cosine v. This one is 2x. The answer, dy dx, should be those 3 multiplied together. Why? Because dy du times du dv times dv dx, the dv dv, the du du would cancel, and that is dy dx, right? That's what would happen. So I multiply these all together, and I get 1 over 2 root u times cosine v times 2x. You're not done at this point, though. You have to replace v with x squared plus 1. Then you have to replace u with sine v, but then replace the v with x squared plus 1. So eventually, once you substitute everything back in, you would get the same answer that we did the other way. All right, what do y'all think? That's 3 different methods. Pick yours, whichever one you want. Wow. Does this seem like a long class? I did not expect to finish chain rule and have like time. Yes?
Will this method work if you have like a, what was just quotient or product?
Mm-hmm.
Will it still work?
Yeah, but that's what you're going to kind of run into in your homework. You're going to see some problems where you're going to... Yes, the answer is yes, it will work. You just have to do it properly. So let me look real quick at this homework assignment. See if there's anything in here that kind of... Yeah, let me make one up.
Will you ask us to use a certain method on the test?
I do not care.
Okay.
Just not a calculator. Like, you know, you have to do it.
Yes.
Yeah. There's a function. Now I'm gonna treat this one as if I've done like 20 homework problems already. I've got basic ideas down, and I'm gonna just kind of attack it the best I can with as little writing down as possible. Or else, are you saying you want to see like the table Leibniz notation type thing? Who asked?
I asked. Yeah, sure, we can show the table.
Okay, all right, so if I was Leibniz at this point, I would realize I have a quotient, okay? I would realize that. I would realize that y is equal to, I don't know, something, u over v, right? That's what I would realize right now. Something over something. And Leibniz would agree that the derivative then would be u prime v minus v prime u over v squared. That's just Leibniz saying it's derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared, right? But when he got to the part where he wanted to know what the derivative of u was, he would have to go figure out what the derivative of this was, right?
Did you do that?
So he would come over here and he would write down u is equal to sine of, right, sine of this? So he would call that sine of m, z, whatever, sine of m. But what's m? X squared plus x. Do you understand what I'm doing here? So he would now take the derivative of each one of these. This one would be d u d m. That would be what? Cosine m. This one would be d m dx, which would be 2x plus 1. He would multiply those two together, and that would represent this top left corner. Right? Do you see how this can become tedious if you don't get good at this shortcut, method 3? Although this is cool, and you can write the little table, and you can kind of go, yeah, if you multiply those, the d, the d whatevers cancel, the dm's cancel, and that's cute. It starts to take forever to do that. So you want to get to a point where you don't need all that. Okay? Should I continue, or is this kind of give you an idea? Then he would have to go after v prime, so he would say, hey, v is equal to, I don't know, q to the 7th, and then q is equal to x cubed.
Pretty soon you shoot through the wall, but
Yeah. Yeah, you're going to run out of letters eventually.
I can see why this method in this instance is slightly better.
The third method is the best, right? Because look, the third method, let's see if we can do the third method. I think we can. All right, I'm going to do it without writing anything down. I do know I need quotient rule, right? I do need that. I need the derivative of the top. So I look at the top. Top is composition. Function, here's a function inside. So I'm going to take a quick little mental derivative of sine of my hand. Derivative of sine of my hand is cosine of my hand. But chain rule says I tack onto that the derivative of what was inside of it, which is 2x plus 1. I need that in parentheses. All right, that is u prime. Agreed? Times v. What's v? All that junk to the 7 minus now v prime. Now v is the bottom, right? So I've got to take this thing to the 7th power. The derivative of this to the 7th. 7 drops out. All of that stuff to the 6th times the derivative of what was there. So now you go inside to the next layer, which would be x cubed, 3x squared plus 1. Then times u. So sine of x squared plus x. I'm probably off camera at this point, but doesn't matter. All of that over the bottom squared. So you could say x cubed plus x minus 1. This time we can say 7 squared, that'd be 14. So see, that would be the derivative without me really even needing to write anything down, right? I mean, I just applied the quotient rule.
That could be ugly.
Yeah.
So when you have quotient and product, if you find the composition function within the product or the quotient, you do those first, and then you expand out with the product and then the quotient, right?
Say it again.
Like when you have a quotient rule or a product rule, but you also have a composition within those products or quotients, you do the composition first.
Well, I did the quotient first here, right? I wrote the quotient down, and then as I did the quotient, I had to do my chain rules.
I guess what I meant you do the composition within the quotient.
Yes, okay, yeah, as long as we understand, yeah, the language you're saying, you're doing the composition within the quotient rule.
Right.
Yes. Mm-hmm. So it's possible to have, these are two compositions within a quotient. How about, can anyone give me a function that would be a quotient within a composition? A quotient within a composition. I did one. Sine x squared plus, I don't know if you meant that.
Yeah, that's fine. Over
Oh.
full over 1. Or
over 9. Yeah, we could do 9, or like how about 9x squared plus 1? There's a quotient inside of a composition. So for this one, you wouldn't set up the quotient part until you got to the end of the chain rule. The chain rule would come first. It would be sine of this, derivative of that is cosine of that, and then times, then you go do your quotient. See the difference between these two? Now look, we're done with class pretty much, but let me just say one thing about this chain rule. The whole goal of Cal 1 is to be able to take derivatives. We start out with the limit, and we realize just how much work that is, right? Just like to take a derivative as simple as y equals x cubed plus 2x using the limit, h goes to 0. That was quite a bit of work. These rules have given us a way to take derivatives quickly. And there are no more rules. This is it. So theoretically, if someone hands you a function, you should be able to take the derivative of it, no matter what it looks like. Right, so there are no other rules that you're going to get that are going to make derivatives any easier. Now, there is some tweaking of it. We use logs and stuff later to help us with taking derivatives, but this is it. At this point, you should be able to take the derivative of anything. Okay? Which is good. So now we can get to work on some other things. Now we can actually apply this to something. But practice, right? You're going to spend all your weekend, I know most of the weekend, doing all your homework and getting caught up. We did not have a quiz this week. Right? So definitely going to have one next week, if not 2. I guess we're done, right? Have a good weekend, everyone. You should bleed chain rule out of your ears this weekend. Yes.
What would be the derivative of an absolute value?
Of just the absolute value